So in this session, I want to pick up a new problem called Fibonacci series. So the problem is that I'm given an n and I need to find nth Fibonacci number. So what is Fibonacci series? Fibonacci series starts with two ones. Some people say it starts from 0, but I'm going to pick it from two ones, right? So the first two numbers are given, 1, 1. The next number is sum of the previous two. The next number is sum of previous two. The next number is sum of previous two. The next number is sum of previous two, and so on. So this is your Fibonacci series. So in a way I can say Fibonacci of n is equals to Fibonacci of n minus 1 plus Fibonacci of n minus 2. Now the optimal way of finding nth Fibonacci number will be to do it iteratively. You take the first number, second number, you find the next number, update first and second, and then basically keep finding the next number. Right? Store the two just before the next one and then keep finding the next number and keep updating these numbers. But here we want to use recursion to do it. It will be not the best solution. The best solution will be iterative, but it will help us understand recursion better. So if somebody asks me to write code for Fibonacci, I'm not going to use this code. But if somebody asks me to use find Fibonacci number, like the nth Fibonacci number using recursion, then I'll be doing this. But this is a very good example to learn recursion. Okay. So this is the formula that we can use, right? This is the equation that we can use. We will need a base case. The base case is that Fibonacci of the first number is 1, right? The first number is 1. Okay. So let's write code for this. Okay, so fib of n, this is not going to work whatever I'm writing, so don't worry about that, but we will correct it in some time. So if n is equal to 1, I'm going to return 1 because that's my base case. If you are going to ask me for the first Fibonacci number, I'm going to say 1. Okay, now I need to find fib of n minus 1. That I can find using my own function by calling fib of n minus 1. And you want me to find fib of n minus 2. And you can actually use your own function to calculate that as well. Because while in an extended form of PMI, you can actually assume, once you have proved the base case, you can assume the hypothesis can be that I'm going to assume 1 to k everything is true and I'm going to use this to prove k plus 1. Let me repeat that. So in case of PMI, we have discussed that I need to prove the base case. Once I have proved the base case, I was saying I can assume that f of k is true. Using that, I was proving f of k plus 1 is true. Extended form of PMI says assume f of 1 is true, assume f of 2 is true, assume f of 3 is true, assume f of k is true. Now using all of these, can you prove f of k plus 1 is true or not is going to define whether you can prove f for all natural numbers or not. Okay, so not just for k, you can assume for everything. That means I have to do it for n, so I can assume it's going to work for n minus 1, I can assume it's going to work for n minus 2. Okay, so before we go to the code again, let's first talk about this extended form a little. Okay, perfect. So we were saying earlier that using 1 I can prove 2, then using 2 I can prove 3, then using 3 I can prove 4, right? Now using 1 you can prove 2. Now to prove 3, what is the harm if we use both of these? Because we have already proved 1 and 2. Can I use 1 and 2 to prove 3? I should be able to do that, right? Because I have already proved 1 and 2. Now when I have proved 1, 2, 3, all 3, can I use these to prove 4? I think I can. Why can't we use all of them when we have already proved them? Why do we have to depend upon just the previous one? So this is basically the intuition behind the extended form of PMI. Okay, so I can assume for n minus 1, I can assume for n minus 2 that my function is going to give me the right answer. Once I have n minus 1 and n minus 2, my output will basically be fib of n minus 1 plus fib of n minus 2. I just named my variables in this way so that it becomes easier to recall what we are trying to do. And then I can return the output. So this function is almost correct. There is a small issue with this function that we will see. Okay, let's try to call this. N is equals to 4. Let's find the fourth Fibonacci number and let's call fib of n. And it seems like it keeps running, but I can say that by looking at the star, and now it has returned and it's saying maximum recursion depth exceeded. That means we kept going in recursion and we never came back. Like it crossed the limit that you are allowed to use. Okay, that's weird because it's a very small input. We shouldn't see this error for such small input. Now what exactly is happening? So you got 4 as your input. For 4 you said, hey, I need 3, and you said I need 2. For 3 you said I need 2. Now it's going to work on 3. Once you return the answer for 3, then it's going to call for 2, right? So first it has to complete this line. Once you're done with this line, then it's going to make the next call. So for now 4 has called 3, 3 has called 2, and it's going to call 1 when it comes back, when 2 comes back. 2 is calling 1 and 0. Okay. For 1 you know the answer, that is your base case. But 0 is not your base case. So 0 is going to call -1 and -2. Wow. And as soon as it goes to -1 and -2, there is no stopping after that. It will keep going down. Recursion will keep growing. So seems like if you call Fibonacci of 2, the first call you make is Fibonacci 1. That works fine because Fibonacci 1 is a base case, it's going to return 1. But then 2 goes ahead and calls Fibonacci of 0 as well. And as soon as you call Fibonacci of 0, things go really bad. Okay? Okay, so what is the solution? In some cases you need to look at, do you require one base case or multiple base cases? In this case we need at least 2 base cases, and I think that's very obvious by looking at the Fibonacci series. If I give you only one Fibonacci number and I tell you find the rest of Fibonacci numbers, I don't think it will be possible, because what you need is, hey, this one has to be sum of this and the one before it. I don't know what is before this. So I think to start the Fibonacci series I need at least 2 numbers. That's required. At least 2 numbers are required. And by looking at recursion and how exactly recursion calls are working, it seems like we will need 2 base cases and not just 1. Okay, so 2 is going to call 1 and it's going to call 0. So either I need to pass the 0th Fibonacci number or I should have the second Fibonacci number, so that when 3 calls 2, it returns directly, when it calls 1, it returns directly, and we don't fall into this infinite recursion problem. Okay, so in this problem we will not require just one base case, we will actually require 2 of them. Sorry, or if n is 1 or n is 2, so there is no 0th Fibonacci number the way I am writing code. There is only first Fibonacci number which is 1, there is second Fibonacci number which is also 1. Now this should work better and we should get the right output, which is the right output. So first Fibonacci number, second Fibonacci number, third Fibonacci number, and the fourth Fibonacci number is 3. So we get the correct answer here. Now let's see how exactly it is working. And again, I want you to notice I've written all the code and now I am asking you to let's see what exactly is recursion doing, what exactly, like how deep it is going, and all of this, how exactly it is working. Okay, so let's say we call for fib of 5. Fib of 5 is going to say, hey, I need 4. That's the first call it's going to make. That's the first call it's going to make. 4 is going to say, hey, I need 3. 3 is going to say, hey, I need 2. 2 is going to say, hey, I need 1. Sorry, 2 won't say anything because 2 is the base case. So 2 will return 1. Now 3 has got the answer for the first call. So 3 is going to make the second call, which is 1, which is also a base case. So it's going to return as well. So 3 gets 1 as fib n minus 1 and 1 as fib n minus 2. So 3 is going to return the output as 2, which is sum of both these sides. Now 4 has the output from one side, from n minus 1. 4 is going to make another call to 4 minus 2, which is 2, and 2 is going to return 1. And now 4 is going to return 3, and 5 is going to say, hey, one side gave me answer which is fine, I need another answer which is 3. So this is in case we had called on 5. We have called on 4, but if it was on 5, this is how things will work. So 5 is saying, hey, I have the answer from 4, that means this is done. Now I need to call this. So it's going to call on 3. Now what is 3 going to do? 3 is going to say, I am not 1 or 2, so let me call on 2. That's the first line here. And 2 is going to return 1. 3 is going to call on 1, which is going to return 1. And 3 is going to return 2, because this is the sum of 2 calls that 3 got. Then 5 will return 5, which is the correct answer for 5th Fibonacci number. So it's doing a lot of work, right? We don't see it, but it's doing a lot of work for us, and it's finding the answer for us. So I particularly like the fact that recursion problems are recursion solutions are very concise, right? Okay, find me n minus 1 Fibonacci number, find me the n minus 2nd Fibonacci number, and then I'll give you the output, and I'm done. I'm not doing much here. I'm just like, it's like I'm asking for things more than what I'm actually doing. But everything is done by me as well. Like all the code I've written here, we have written that code. So nobody else has written this code. But this is a very smart code which basically does all the work for us without we having to think of the nitty-gritties. Okay, perfect. So in the next session, we'll start looking at a little more interesting problems around arrays and how to use recursion along with arrays. Or I can say lists. Okay, thank you.